my capstone project is comparing models and data sets for classifying misinformation. More on what that means later. So misinformation is promoted by bad actors, and it's a huge problem in society. If you live in like Europe or India, your chances are you or your parents use WhatsApp, and especially on that platform, misinformation, fake news, and like these really frustrating WhatsApp forwards that contain bad advice on medicine or political views is really common, and it spreads really quickly through forwarding. And researchers from all over the world have already identified this as a huge problem, and they've been trying to apply machine learning to solve this problem. And while right now there's not much I can do to really work on the cutting edge of that field, I want to see what type of data and what type of models are best for building the best model to solve this problem. Because among these researchers, there isn't exactly a lot of agreement on what type of model to use. Some of them use BERT, some of them use BART, some of them use something else. And there isn't, and most of all, there isn't agreement on what type of data to use. There's like all types of data sets compiled by all types of people. Some of them are really long, like 9 million rows long. This is not something I could have tested, but that's one example. Others are shorter, only a couple hundred. And there's also different types of features in each of these data sets, all towards the same goal. Okay, so roadmap. So let's take a look at the data. So the first data set is called LIAR. It's from the ACM, which is like a prestigious society. And it has more features. So it has, of course, the text of a statement. That's only 20 to 25 words. So it's short text, but it also has the person who said it, their position. So if they were like a president or state representative, etc., their state, like what state they're from, if that's available, and what party they're from. So Democrat, Republican, or independent. Now, there were many gaps in this data, as you could probably guess, because you don't always know which state someone's from or which party they're affiliated with. So that led to me having to remove a lot of the rows. The second data set is from the University of Victoria in Canada, and it has less features. The only features it has is the category of like news it's in. So like whether it's political, world news, etc., the text of the news, and the title of the article. Now, instead of having 20 to 30 words like the LIAR data set, the dataset 2 ISOT is what I'm going to refer to as, had like 700 plus word articles. So it was much longer text, but less like meta features that describe it. So this is how the LIAR data set looks like. You can see here, can you see my mouse? Okay, so you can see here, there's text, which I have processed, and there's the topic, person, the position, the state, the party. This you could ignore, and also the context. The ISOT data had, of course, the title, but also had the text and subject, and also the date. So it had some things that a LIAR didn't have, but overall, less features. So the pre-processing was similar in both data sets, although the arrow is brown chat at the bottom. So first you load the data, one with the TSV, not that hard, basically the same as the CSV. Then I use the NLTK library to remove stop words. Now stop words are basically like useless words in a sentence, like as, to, not super important vocabulary words that you want to be focusing on. So these are words that just clutter the data, and you can remove them so that the model has to spend less time looking at these useless words. Then I removed special characters like parentheses and also punctuation. So question marks, exclamation marks, not super useful for the model. And also any like URLs, because those are not useful either. Then I combine all the useful features into one column. So if you go back, you can see all these features. I put them all into one column with the text. Similarly here, I put the title into the text along with the subject. So that all becomes into one column. Then in models that used LSTM, like LSTM based, I used a Keras tokenizer that just comes to Keras. And in models that were based on BERT, I used the BERT tokenizer. And the BERT tokenizer and model were a lot slower when they were running. And Colab notebooks, which is what I ran everything on, don't have enough RAM in the default mode to actually to run the full BERT model on all the data. So I had to severely truncate the data from 44,000 lines down to only 2,000. And say 44,000 rows down to only 2,000, because the articles were also pretty long, which I had to truncate those a little bit too, but not that much. Okay, so in the end, I created 4 models. One is using the liar data set with LSTM based model. One is liar with a BERT based model. One is ISOT with the LSTM based model, and one is ISOT with the BERT based model. Now, keep in mind, I did use LSTM with the output of the BERT model. So it's not like I only use LSTM and only in the LSTM model. But the LSTM model had more layers of LSTM. So yeah, I tested the accuracy using validation split. So I had a 0.1 validation split, and it gave a validation accuracy while the model was fitting. And before I move on, LSTM is an RNN algorithm layer that is generally considered to be better than base RNN, but by some not considered to be as good as BERT. Well, we'll see how that does. So, a quick visualization of data. There's not much to visualize here, but you can see how much true and false there was in each. So in liar, there was more true data, and in ISOT, there was more false data. And you can also see that there's like 10 times more data in the ISOT. And say I see over 20,000 per class compared to liar. Okay, so the LSTM based models were based off of a baseline that I found on Kaggle. A lot of the code was copied, and this I think is pretty much the unchanged baseline, but I made changes to it eventually. So there's an embedding layer, then there's 2 LSTM layers with a ReLU activation function and a TANH recurrent activation, and then there's a dense with ReLU, and then finally there's a sigmoid. I was told that you should use sigmoid at the end because it messes with your data a bit. The BERT models used the BERT-based uncased model pre-trained. So that's the first step, and then I put it into LSTM followed by a dense layer. So not as much LSTM and dense, but there was a pre-trained BERT model working. Okay, so the overall performance was this. The ISOT plus LSTM performed by far the best with 96.46% validation accuracy and 96.31% test accuracy. The baseline model performed with 99.2. So the changes I made from the baseline didn't exactly make it better, but there wasn't much space to improve from the baseline. Liar plus LSTM did not do that well. It was only 60.44% val accuracy, and we'll look into why that was later. Liar plus BERT only had 46.85% val accuracy, which is basically the same as guessing. And something went wrong with ISOT and BERT probably because the ISOT data was too long and it gave a 0% accuracy. Pretty much it just gave up halfway through. So the progression of tuning was this. The first time I did ISOT plus LSTM, which is the top performing model, it only had 69% accuracy. The changes I made was I removed the sigmoid functions from the beginning, and that put it back up to 80%. Then originally I had expanded the number of epochs from the baseline model from 15 to 30, but that actually made it worse. And once I reduced the number of epochs, it went back up to 96.49%. Another thing I removed from the baseline model is it used a glove. It used a glove to encode the text. I did not do that, but it didn't seem to make too much of a difference in terms of the accuracy. This is only 3% less than the baseline model. Then in liar plus LSTM, which was the second most, originally it was 54%, which is almost guessing. And then I took out the sigmoid functions from the beginning and it got better. So here's some of the limitations or errors that I may have made. I used the same LSTM model on the liar and ISOT datasets when they were clearly different datasets. So a different model might have worked better on liar, and maybe liar in fact is the better dataset. There wasn't enough RAM to train the BERT model on all 44,000 articles in the ISOT dataset, which may have led to BERT underperforming in the accuracy because there simply wasn't enough data to feed into the model. The BERT output was also thrown directly into an LSTM model, and BERT-based encase BERT-based encase is useful for text classification. It's not, however, on its own super useful for text classification. And there, like for example, in the IMDb example, K-train was used along with the BERT-based encase model. The liar dataset also had several blanks, which means that it was not as effective in ISOT in giving large amounts of data to the model. And the liar data set was harder to discern. I think this is the most important thing, that when you looked at an article in the ISOT data set, you could probably tell with your brain whether it was true or not. With liar, these statements are mostly made by politicians, and they tend not to say things that are clearly lies. Instead, it's like half lies or half truths. So that's harder to tell with only the knowledge that you have, whether it's true or not. So it's harder to classify data that's like that. So conclusions. The best model was ISOT plus LSTM. It performed 160% better than the liar data set with the same model. It's necessary to use other approaches for shorter data, like the one in liar, that has more meta features, regardless of whether it has more features. I can't really think of what new approach we would use for things that are harder to tell with your own brain, but that's what the latest cutting edge research is trying to solve. The performance of BERT was inconclusive because I feel like BERT could have been given more justice by the code that I used, but for now it did not perform as well as LSTM. I also have some personal conclusions. So machine learning takes time, both to learn for yourself and to train your models. And not everything is in your control when you're making a model. A lot of it feels like wizardry and a lot of it's up to chance, especially with like the data you get. Cleaning the data is a lot, if not most of the job. I feel like that's not the perception of machine learning as a field, but yeah, you spend a lot of time cleaning the data. And when you're not cleaning the data, you're doing lots of experimentation with your model, seeing what works, seeing what doesn't work. And it's also very resource intensive, and Colab Pro therefore exists for a reason, so that you can get those resources, and the default version may not be enough. So despite all of this, that's all okay, because in the end result, you can do some really amazing things with once you get the right model in hard work. So that's end. I have no more slides. Any questions?